Okay, so today we're going to start on a new topic, and this is MOS transistors. MOS stands for metal oxide semiconductor. MOS transistors are field effect transistors, so we also call them MOSFETs. This is what I intend to cover this next two meetings, that's today and on Thursday. First, I'm going to give you an overview of transistors. Then I'm going to discuss the simplified structure and theory of operation of the NMOS transistor. Actually, yung structure and theory of operation, hindi talaga yung kasali sa EEE 123. No? That's taken up in EEE 131. But I just wanted to give you a rough idea of how a MOS transistor works. No? So if you don't understand this part, yung theory of operation, don't worry about it. No? What's important is that you know the models. Okay? So after that, we're going to go to the VI characteristics. Then I'm going to discuss the operating modes and the corresponding models. So this is the important part of the course coverage. And then we're going to go into DC analysis of NMOS circuits. Then I'll go into a discussion of the NMOS transistor as an amplifier and the NMOS transistor as a switch. So that is going to take up 2 days. Okay, first, I want to give you an overview of field effect transistors. So we started our journey in transistors with a discussion of the bipolar junction transistor, or BJT. No? Actually, there are 2 general types of transistors. You have the BJT and you have the FET, or field effect transistor. The BJT, it's bipolar because current is due to both electrons and holes, no? Or electrons, negative charge carriers and positive charge, negative charges and positive charges, no? And then itong field effect transistor, you call it a unipolar transistor because your current is either due to electrons or positive charges. Now, field effect transistors, there are also 2 general types: the JFET, the junction field effect transistor, and the metal oxide semiconductor field effect transistor. No? So we're going to focus on this in this particular course. Now, MOSFETs, there are also 2 general types. You have your enhancement type and you have your depletion type. So dito tayo sa depletion type. Okay? And we will be focusing our discussion on N-channel depletion type MOSFETs, no? Or NMOS per short. In EEE 131, you're going to take up the enhancement type, and you're also going to do more work with the P-channel. No? Pero dito sa 123, ito lang muna yung patikim namin sa inyo, no? Tungkol sa mga MOSFETs, mostly N-channel NMOS transistors. Okay, I wanted to present to you a simplified structure and the theory of operation of the N-channel MOSFET. So I came up with a few slides for that. If you take a look at the structure of a MOSFET, in particular an N-channel MOSFET, take a look at the top view. This is what you're going to see, top view. Okay. And if you get a cross-section of that structure, so a cross-section along here, this is what you're going to see, the cross-sectional view. So what are the different parts of your MOS transistor in this particular case? You have the substrate. So this is a semiconductor. And for an N-channel, this is a P-type. So I don't know if you attended my lecture where I gave an introduction to the types of bipolar junction transistors. So I discussed there that there were 2 types of semiconductors. You have an N-type and a P-type. So the N-type, your charge carriers are electrons, and the P-type, your charge carriers are positive charges. So in your N-channel MOSFET, your substrate is a P-type. Okay, so top view, ito yon. Okay. And then you have N-type islands that are diffused into the substrate. No? So you might consider this like an island that is diffused on the substrate. No? So that's diffused in this area from the top and also in this area. Okay, so from the top, that's diffused, and then it penetrates toward the bottom, and this is how it ends up. And then in the middle, no, between the two islands, what you have is, first you have a layer of silicon dioxide. Silicon dioxide is actually an insulator. Actually, it's a form of glass. If you take a look at it under a microscope, it looks like glass. And then on top of your silicon dioxide, you have polysilicon. Polysilicon is silicon, but polymorphic, no? or not a single crystal structure. And the characteristic of polysilicon is it acts like a conductor. So it is really this really just acts like a simple conductor. And then you have metal that is deposited. So this is metal. You also have metal here, and you have metal here. And on that metal, you have your contacts. So these are now your contacts or your terminals. Okay. So this is the cross-sectional view of your N-channel MOS transistor. Okay, I redrew here the cross-sectional view. The polysilicon, in the early days of electronics, what was used instead of polysilicon was actually also metal. No? So you have polysilicon, formerly that was metal. Then underneath the polysilicon, you have your silicon dioxide or your oxide, which I said is a conductor. And below that, you have your semiconductor. So this structure, polysilicon oxide semiconductor, that is why it is called MOS, no? Metal oxide semiconductor. This is actually a capacitor. This is the structure of a capacitor. A capacitor consists of parallel plates. So the polysilicon, this is one parallel plate, conducting plate. Your semiconductor is your second conducting plate. And then between your two plates, you have an insulator, which is your silicon dioxide. So that is your MOS structure, metal oxide semiconductor. Okay, so you have terminals that can access the different parts of your transistor. So here we have a terminal. We call this the source. Here we call this the drain. And here our terminal giving access to the capacitor is what we call our gate. So the capacitor terminals are actually the gate and the substrate, or what we call the bulk. The substrate, we also call it the bulk. So this is your simplified structure of an N-channel MOSFET. Now, the reason why we call it N-channel, you're going to find out soon. Okay, are there any questions with regard to this construction? Okay, just some interesting facts that I wanted to mention. Most of the electronic components nowadays use this type of transistor rather than bipolar junction transistors. I mean, bipolar junction transistors, they still have a lot of use these days. There are still a lot of applications that use them. But most of the integrated circuits, if you take a look inside, uses this type of transistor. And the reason for that is it occupies less space than a bipolar junction transistor. For example, the iPhone 12, if you go inside the iPhone 12, the main processor of the iPhone 12, you call it the A14 bionic chip. This was designed and is fabricated for Apple. And the size of that chip is 88 millimeters squared, 88 square millimeters. There are 11.8 billion transistors in that chip, 11.8 billion transistors. And most of these are MOSFETs. Most of these are MOSFETs. The minimum feature size, or the width of the smallest transistor in the A14 bionic chip, is 5 nanometers. 5 nanometers, that is 5 times 10 to the minus 9 meters. Okay, how small is that? Well, for example, your hair, yung buhok natin, typically that is about 50 to 70 micrometers, no? 50 to 70 micrometers. Okay, so if you consider 5 nanometers, no, in the width of your hair, you can actually fabricate in the width of your hair thousands of transistors, thousands of MOS transistors. So that's how small these transistors can be in integrated circuits. And if you take a look at the A15 chip, that is the chip that is now used in the iPhone 13, there are 15 billion transistors. And the M1 chip, that is the chip that is used in the latest MacBooks, there are 16 billion transistors. So that's how small these transistors can become. Okay, let's discuss briefly the theory of operation of your MOS transistor. Okay. If I apply a voltage between my drain and my source, no? So I said, one terminal I call my drain, the other terminal I call my source, and this terminal I call my gate. No? And my gate to substrate is actually a capacitor. If I apply a voltage between my drain and source, with my drain positive with respect to my source, I should expect the current to be zero. Now, why will this current be zero? Okay. If you take a look, I have two junctions. No? I have a PN junction here, and I also have a PN junction here. No? If you recall, a PN junction is a diode. So what I have actually, between this P and this N, I have a diode in this direction. Okay. And then between this P and this N, I have a diode in this direction. So this is what my circuit looks like. My circuit looks like a power supply. Then I have a diode this way, and I have a diode this way. So what will my current be? This diode is going to be reverse biased because the current is trying to flow opposite the direction of the diode arrow. So this diode is going to be reverse biased. Because this is reverse biased, the only thing that will flow would be your leakage current. In fact, for all practical purposes, your current is approximately equal to zero because your leakage current, as we had studied when we studied diodes, is in the order of nanoamperes to even femtoamperes. Okay. Okay. So this is going to be equal to zero. By the way, no, typically we ground the bulk, no, or we ground the substrate. And the reason why we ground the substrate is we want to prevent current from flowing from the source to the substrate or from the drain to the substrate. No? By grounding the substrate, essentially we are making the P negative with respect to the N. No? And therefore, it's going to be like a reverse biased diode. So that's why we ground the substrate. Okay, what will happen if I apply a voltage between my gate and my substrate? No? So my substrate is grounded. My substrate is grounded here. No? I apply a voltage between my gate and my substrate. By the way, my source is also usually grounded. So this ends up being a gate to source voltage. If I apply this voltage, an electric field is going to build up here in this oxide layer. There's going to be an electric field in the oxide layer. Remember, this is a capacitor. Now you don't know yet what a capacitor is. You haven't studied it yet, but some of you might be familiar with a capacitor from maybe high school or from physics. No? So there's going to be an electric field here. And what will this electric field do? That electric field is going to cause electrons existing in the substrate to be attracted to this region. So yung mga electrons dito sa substrate will be attracted to the region. Now, the substrate is a p substrate. So actually, we don't expect there to be many electrons in the substrate, no? Because the substrate being p means that charge carriers in the substrate are positive charge carriers. But there will always be what we call minority carriers. You're going to learn that in EEE 131. No? There will always be what we call minority carriers. These are carriers that are produced thermally. And these carriers are going to be attracted now. These electrons are going to be attracted to this area. Okay. If VGS is large enough, if this voltage is large enough, because the electrons were attracted to this area becomes an N-type. So dati-dati P-type siya dahil madaming electrons pumunta sa kanya. Okay? Unang-una, man-neutralize yung mga positive carriers. And then, as more electrons come, it changes from being a P-type to an N-type. So this becomes an N-type. This area becomes an N-type. And we call this a channel. We say a channel has been enhanced underneath the gate. That's why this is called an enhancement type MOSFET, because you're enhancing a channel underneath the gate. The voltage needed for this channel to exist, we call that VTH, the threshold voltage of the transistor. This is the minimum value of VGS that creates what we call this inversion layer or this channel. If VGS is less than VTS, you don't have an inversion layer. It is when VGS is greater than or equal to VTH that you have an inversion layer. Okay, so anong significance nitong inversion layer na to, no? If we now have that layer and we now apply our voltage here, no? Remember earlier, wala itong VGS. When we applied VDS, ID was equal to 0. Now with VGS here, if I apply my voltage here, because I have a contiguous N region here, I can now expect current to flow. So current is now going to flow this way. We call this I sub D our drain current, and this is going to be greater than 0. So the presence of a channel allows current to flow if VDS is applied. And the current that will flow is due to electrons because this is N-type. This is N-type, so the charge carriers here are electrons. So actually, electrons are going to flow from the left to the right. If current is flowing from right to left, that means electrons are flowing from the left to the right. And that's why you call this the source, because the source is your source of charge carriers. Doon ang gagali yung charge carriers. Your electrons coming from here, going here. Or that is a current in the opposite direction. So you notice now that we can use this voltage to actually control this current. Because the larger this voltage, the more electrons attracted to this region, and the more charge carriers you have. So VGS can be used to control the flow of current. Okay, so that is your N channel, no? So I just want to mention this. If you have an N channel, you have a P channel. So the N channel, we also call it an NMOS, and N metal oxide semiconductor transistor. The P channel, we call it the PMOS. In the P channel, your substrate is N-type, instead of P-type. Your islands, your source and drain islands are P-type. Okay. Then everything else is the same. And then to make this work, the voltages that you apply are opposite in polarity to your NMOS. So you apply, instead of applying a positive voltage here between gate and source, you're going to apply a negative voltage between gate and source. That negative voltage is going to attract positive charge carriers here underneath the gate. And then if that voltage exceeds the threshold voltage, this is going to be now a contiguous P-type. So the channel that will be enhanced underneath the gate will be a P-type. And if you now apply a drain to source voltage, current will flow. And the flow of current will be due to the flow of positive charges. Okay, are there any questions so far? Any questions? I hope you've been able to keep up. These are the circuit symbols for your MOS transistors. We have two symbols, one showing the bulk and the other not showing the bulk. No, the bulk is the substrate. Okay. When B is connected to S, then this is usually the symbol that we use. And this is the symbol that you see all the time, no? Because the bulk is normally connected to the source. So this is your N channel or NMOS, and then this is your P channel or your PMOS. Okay. So the arrow appears at the source terminal and indicates the direction of current flow at the source. No? So here at the source terminal, we know that the direction of current flow will be going outward. Here at the source terminal, we know that the direction of current flow will be going inward. Okay, let's discuss the VI characteristics of your NMOS. So we're going to be focusing, as I mentioned earlier, we're going to be focusing on the NMOS. Let's discuss the VI characteristics. What are these characteristics? That is a plot of the current ID that will flow with VDS. So I vary this. I vary this VDS. I take a look at the current that will flow when this is fixed. Of course, VGS has to be greater than the threshold voltage because a channel has to exist. A channel has to exist. No? For your channel to exist, VGS should be greater than VTH. Okay, what will happen if I start from 0 and start increasing VDS? Okay, this channel acts like a resistor. Initially, this acts like a resistor. So what are the characteristics of a resistor? If you increase the voltage, you increase the current. No? Ohm's law, V is equal to IR. So you increase the voltage, you increase the current. No? So we call this the linear mode of operation. No? So notice that as you increase the voltage, you're increasing the current. Now, it is not really a linear resistor. A linear resistor is a straight line. This particular case, it curves a bit. No? It curves a bit. But largely, your voltage will be increasing with your current. So we call this the linear mode of operation, sometimes also called the triode mode of operation. Okay. Actually, VDS will have an effect on the shape of your channel. If you notice here, the way I drew my channel, it narrows as I get from the source to the drain. And the reason why it narrows is VDS has an effect on the electric field across your oxide layer. Okay, again, no, you may not. It's okay if you don't appreciate this fully now. It's going to be taken up in more detail in EE 131. But this affects the electric field across your oxide layer, such that the electric field across your oxide layer here is going to be smaller than the electric field across your oxide layer here. No? Dahil mas malapit dito yung positive terminal ng VDS kaysa rito. And that's why ang nagiging shape ng channel natin medyo nagnanarrow siya dun sa drain end. Okay. The oxide layer voltage must exceed VTH. No? So the voltage across this oxide layer must exceed VTH for a channel to exist. Now what will happen? No? If we continuously increase VDS, no? Continuously we're increasing VDS. Okay. So continuously lumiliit yung electric field dito. Paliit ng paliit yung electric field dito. Now, up to the point where the electric field here will disappear. And when the electric field here disappears, then we say that our channel now has been pinched off. We say the channel has been pinched off. No? So ito yung pinch off niya. No? Kasi habang lumalaki yung VDS, sabi natin, lumiliit yung electric field dito, so yung channel dito nawawala. And that's what we call pinch off. And when that happens, increasing VDS further will no longer cause an increase in your drain current. So increasing VDS further will not increase anymore your drain current. Your drain current will stay more or less constant. And we call that now saturation mode. We call that saturation mode. And when does that happen? That happens at this point. No? That happens at VDS sat, where VDS sat is equal to VGS minus VTH. So for different values of VGS, it will happen at different points. No? So VDS sat is dependent on VGS and your threshold voltage VTH. So this is now your characteristic curve. So this is only for one particular value of VGS. These are your characteristic curves showing several values of VGS. No? So this is for one particular value of VGS. This is for another value of VGS. This is for another value of VGS, and so forth. So when does it transition from linear mode to saturation mode? It transitions from linear mode to saturation mode here, no? When it reaches VDS sat, which is a function of VGS. No? So that's more or less dictated by this dotted line. No? This dotted line will show you where the transition is from linear to saturation. So for this value of VGS, it will happen here. No? For this value of VGS, it will happen here, and so forth and so on. So this is going to be your linear mode, and this is going to be your saturation mode. Now, when VGS is less than VTH, what is again VTH? VTH is the voltage from your gate to source that will cause an inversion layer. When VGS is less than VTH, then you're cut off. You don't have any current that will flow because you don't have any inversion layer, or you don't have any channel underneath your oxide. Okay. So this is the direction of increasing VGS. Ano? This is increasing VGS. So itong VGS na to, mas malaki rito. Itong VGS na to, mas malaki rito, and so forth. Okay. I want to point out one thing. Ano? Sa BJT, if you recall, sa BJT, we also had our characteristic curves, which is a plot of IC versus VCE. And the curves look very similar, no? The curves look very similar, if you recall, no? Ganun din siya. The thing I want to warn you about is sa BJT, okay, what is this operating region? Do you remember? Can somebody tell me? What is this operating region in the BJT? Nakalimutan na ninyo?
Saturation po.
That's right, no? In the BJT, this operating region, this is saturation. And then anong tawag dito sa region na to?
Forward active.
That's right, no? This is active, no? This is active. Okay, sa MOS, kung ano yung saturation sa BJT, yun yung linear, no? Yun yung linear. Okay? And then kung ano yung active dito sa BJT, yun yung saturation dito sa MOS. So there's sometimes that confuses the student, ano? But you keep that in mind, ano? So sa MOS, yung linear region corresponds to the saturation region in your BJT, and sa MOS, your saturation region corresponds to the active region in your BJT. Okay, so I summarized here the operating mode equations for NMOS. No? So we're not going to go through the derivation of these equations. In fact, kahit sa EEE 131, no, hindi na ginagawa yung derivation. Nung unang tinuturo yung 131, I was part of the group that first taught 131 in EEE. We actually went through the derivation of these equations, no? But actually, to be honest with you, I never thought that it would be appreciated by the students. So now hindi na ginagawa din sa EEE 131. So if you're interested in the derivation, this appears in the textbooks, no? In the references that we mentioned, no? So you can look it up. What's important is the expression or the model, no? So when your MOS is cut off, that is when VGS is less than VTH, your drain current is equal to 0. Okay. When your VGS is greater than VTH, there are two possibilities, no? When VGS is greater than or equal to VTH, there are two possibilities. It's either in linear operation or in saturation. Okay. When is it in linear operation? That is when VDS is less than VGS minus VTH. No? If you will recall, this is VDS SAT. No? Itong quantity to, VGS minus VTH is equal to VDS SAT. No? VDS saturated. So this is VDS saturated. When VDS is less than VDS SAT, then you're linear. When VDS is greater than VDS SAT, then you're saturated. In saturation, this is your formula for drain current. Your drain current is only dependent on VGS. It is not dependent on VDS, no? And that is obvious from here, no? If you take a look at this drain current, okay, it does not depend on VDS. It does not depend on VDS. Kahit na anong value ng VDS dito, pareho pa rin yung current dito, no? It only depends on VGS. So in saturation, your drain current is, the formula is 1/2 K VGS minus VTH squared. 1/2 K VGS minus VTH squared. It only depends on VGS, no? VTH is a parameter of the transistor. Pag nasa linear region naman, so in this region, in this particular region, your drain current is a function of both VGS and VDS. No? So meron akong VGS dito, meron din akong VDS dito. So it's a function of both VGS and VDS. No? So I sub D is a function of two variables. Dito, I sub D is only a function of one variable. So that leads to the following models. So again, no? Ito na yung importante sa 1, 2, 3, that you use the proper model when you try to analyze the circuit. So that leads to the following model. So cut off, when VGS is less than VTH, this is equivalent to this. Okay, note that I sub G will always be equal to 0. No? Basta't DC ang voltages natin, I sub G will always be equal to 0. Why is that so? No? Let me go back to this construction. No? Malayo na pala. No? Let me go back to this construction. Remember, this is an insulator. No? Itong silicon dioxide layer or oxide layer is an insulator. If that is an insulator, ibig sabihin nun, even if we apply a voltage between gate and bulk, at steady state, no current will flow because your current cannot flow through an insulator. And that's why we say that I of G is always equal to 0 for DC at steady state. So let me go back to that slide. Here. Okay. I of G will always be equal to 0. Now, when VGS is less than VTH, there is no channel, or there is no inversion layer under the oxide. So you also have an open circuit between your drain and source. In effect, your transistor is just open everywhere. No? I of G, which is I of D, which is I of S, they'll all be equal to 0. Okay, when your transistor is in saturation, so ano uli yung conditions for saturation? First of all, VGS has to be greater than the threshold so that you have an inversion layer or a channel. And VDS should be greater than VDS SAT, no? Where VDS SAT is VGS minus VTH. In other words, nandun ka sa kanan nung graph, ano? Your VDS SAT is that vertical line, and then you're on the right side. You're in saturation. So what is your transistor now? Your transistor now is equivalent to a voltage-controlled voltage source. Voltage-controlled current source. So this is really a voltage-controlled current source. Unfortunately, it is not a linear element, no? Because you have a squared relationship here. So hindi siya linear element. Your gate is still an open circuit. I of G is equal to 0. Now, because your gate is an open circuit, whatever current flowing into the drain will also be the current flowing out of the source. No? In other words, I of D will always be equal to I of S. And this is your formula for I of D. 1/2 K VGS minus VTH squared. No? By the way, yung K is a parameter of the transistor. No? This K. Okay. So the K and VTH, these are transistor parameters. So you find this in the technical data sheet of the transistor, or for example, for integrated circuits, that will be part of the process parameters that the fabricator will give you, no? K and VTH. K, sometimes we call K your process transconductance. So ito yung saturation. And then the third model, linear model, okay. So these are the conditions now. VDS should be less than VDS SAT here. And effectively, your channel acts like a resistor. Okay, the value of that resistance being RDS on. RDS on. Note that this is not a linear resistor, because that resistance changes depending on the current flowing or the voltage across it. So this is not a linear resistor. No? RDS on is not a linear resistor. No? The value depends on the current that flows through it. So habang nag-iiba yung current, nag-iiba din yung value ng RDS on. Hindi kagaya ng resistor na alam natin na kahit na ano yung value ng current, the value of the resistance stays the same. Okay, there's a way of determining RDS on. So remember that in the linear region, this is your formula for I sub D. No? So this is our linear region. No? Ito yung VDS SAT. Ito yung VDS SAT. So our linear region is the area on the left. No? Okay, depending on the point we're operating, nagbabago yung resistance. Ano? Because resistance is actually just the slope of, let's say we're operating here at this point. We're operating at this point. What is your resistance? Your resistance is actually VDSQ over IDQ. No? Where Q is your Q point or your operating point. No? Or your resistance is actually just the inverse of the slope of this line. No? And depending on where we're operating, the slope of this line changes. That's why your resistance changes. I can derive an expression for RDS on. No? RDS on is just VDS over ID. So here, from here, I get an expression for VDS over ID, and this is what I'm going to get. No? So yung ID ilalagay natin dito sa baba, ito ilalagay natin sa kabila. This is what I'm going to get. So my RDS on here is dependent on VDS at the operating point. At the operating point. So to determine RDS on, I should know what point I'm operating at. No? Kung gusto kong i-compute to, dapat alam ko where exactly in this curve I'm operating at. But sometimes we just want to make an approximation. Sometimes you just want to make an approximation. And usually, your value of VDS is going to be small with respect to VGS minus VTH, usually. So for small values of VDSQ, small values of VDS at the operating point, I can just neglect this, and this is going to be my approximate value of RDS on. So this is just to approximate what the value of this resistor is going to be. But if you know the operating point, kung alam mo naman yung value ng VDS, at the operating point, we call that VDSQ, then you can have a more exact expression for RDS on. Are there any questions so far? Any questions? Okay. So basic steps in analyzing NMOS circuits. So you recall sa BJT we had guidelines that we published how to analyze BJT circuits. The same thing for NMOS. So the first is determine VGS from the gate circuit knowing that I sub G is equal to 0. So yung unang gagawin, ano? Determine VGS from the gate circuit knowing that I sub G is equal to 0. And then we compare VGS to VTH. If VGS is less than VTH, tapos na yung laban, ano? Alam na natin cut off. If VGS is less than VTH, we already know that the transistor will be cut off. So we know that I sub D, which is equal to I sub S, is going to be equal to 0. And therefore, we can compute whatever other quantities we need to compute for knowing this. Now, if VGS is greater than or equal to VTH, then there are two possibilities. It's either it is in saturation or it is in linear mode. So we usually assume first that it is in saturation. And the reason why we do this is the saturation equation only depends on one variable, that is VGS. So the computation is going to be easier. So ang unang assumption natin usually is that we assume that the transistor is saturated and that we can use this particular formula for I sub D. So we use this formula for I sub D knowing VGS kasi na-compute na natin yung VGS dito sa step 1. So alam na natin yung VGS, so mako-compute natin yung I sub D. And then knowing I sub D, we can compute for VDS by applying KVL to the drain to source path. After computing for VDS, we have to check our assumption. So how do we check our assumption? We compare VDS to VDS SAT. Ano yung VDS SAT? That's VGS minus VTH. If VDS is greater than VDS SAT, tama yung assumption natin. Tapos na. No? The value that we got for I sub D is valid. But if we find that VDS is less than VDS SAT, then we know our assumption is wrong. And we know that instead of being in saturation, it is in linear mode. And therefore, we have to change our formula to the formula for ID in linear mode, which is this. Okay. Unfortunately, this is a more complex formula because ID is a function of both VGS and VDS. Usually, we have to combine this formula with another formula, the formula for KVL along the drain to source path, to determine the value of I sub D. So that's how you analyze an NMOS circuit. And what better way to do to illustrate that than through an example? So here I give an example. The transistor has a value K, which is 0.25 milliamperes per volt squared, and VTH equal to 3 volts. No? So what I want to do is I want to determine the value of ID and Vout for all of these input voltages. So this is my circuit. It's a very simple circuit. I just have an NMOS transistor, a drain resistor connected, no? And then a power supply voltage of 12 volts. And then I'm getting my output here. Notice that my output is actually equal to VDS. No? Remember, this is my drain, and this is my source. No? So Vout is actually equal to VDS. And Vin is actually equal to VGS. No? Because this is my gate. No? So Vin is actually equal to VGS. Okay. So I want to determine the output voltage for various input voltages. Let's start with Vin equal to 0. What is my ID going to be? Anyone? Ano yung magiging value ng ID ko when Vin is equal to 0? Can someone shout out the answer?
Zero po.
Yes. Can you explain why 0?
Kasi po yung VGS po is less than the VTH. Kaya po yung
That's correct.
nasa cut-off po siya. So, 0 po yung ID.
So, because our input voltage is less than the threshold voltage, the threshold natin is 3 volts, ano? Then our current ID is equal to 0. And therefore, what is Vout? Can you continue? What is Vout?
12 volts po.
Yeah, Vout will be equal to 12 volts. No? Kasi pag ID equal to 0, ibig sabihin wala kang voltage drop dito. So kung ano man yung voltage dito sa VDD, yun din yung magiging voltage dito sa Vout. No? Okay. What about when Vin is when Vin is 2 volts? No? Ganun din, ano? Yung Vin natin, 2 volts, hindi pa rin umaabot sa 3 volts. So this is still going to be 0, and this is still going to be 12 volts. Okay. What now if Vin is equal to 4 volts? Yan, ibang usapan na yan. No? Vin equal to 4 volts. Kasi yung 4 volts natin ngayon, mas malaki na sa threshold. So since mas malaki na yung input natin sa threshold, then expect yung ID hindi na magiging 0. No? So let's analyze that. Ano? At Vin equal to 4 volts. So according to our rule, okay, determine VGS. Well, alam na natin yung VGS. No? VGS is Vin, which is 4 volts. We already know that that is greater than VTH. So andito na tayo sa step 3. We assume the transistor is saturated. So we assume saturated, I can compute for ID. Okay, this is 1/2 K VGS minus VTH squared. Okay, this is 1/2. Ano yung value ng K? K is equal to 0.25. Sandali, no? Sorry. Can I make a correction dito sa... I'll make a correction sa slide, no? Made a mistake here. This is supposed to be 0.5. No? Yeah, that's supposed to be 0.5, sorry. So IS of D is 1/2 K VGS minus VTH squared, no? So that's 1/2 times 0.5, no? VGS is 4, VTH is 3 squared. No? And I'm going to get IS of D is equal to 0.25 MA, no? Because 4 minus 3 is 1, 1 squared is 1. So 0.5 divided by 2. Remember, this 0.5 is milliamperes per volt squared, no? So IS of D is going to be 0.25 MA. Okay. But don't assume na tama na yun, ano? Huwag muna nating ilalagay dito because we have to check our assumption. Okay, how do we check our assumption? Okay, first, let's compute for VDS, no? VDS or Vout, no? Vout is equal to VDD minus ID times RD. Okay, minus ID times RD. What is this, no? This is going to be 12. VDD is 12 minus 0.25 times 2. No? Or this is 11.5 volts. 11.5 volts. Now we check the assumption. Check. Is VDS greater than or equal to VGS minus VTH? In other words, nasa kanan ba, no? Yung VDS, nasa kanan ba ng VDS SAT, no? VGS minus VTH. Ang value ng VDS natin is 11.5. Ang value ng VGS natin is 4. And VTH is 1. So yes. Tama, no? 11.5 is greater than 4 minus 1. So yes, ibig sabihin, assumption correct, no? Assumption is correct. So tama yung value ng 0.25 MA dito. And tama rin yung value ng 11.5 volts dito. Okay? Nasundan nyo? Okay. Can I ask you, no? Para lang ma-exercise kayo, can I ask you to do the next one? I'll give you several minutes. Try to do the next one. What is the value of ID and Vout for V in equal to 6 volts? And then if you've done it, can you just enter your answers chat box so that I can see if you've been making progress. Okay? Please try, no? The only way you learn is if you try, no? Don't just wait for the others who are attending this session to do it. Please try. I already have one with an answer. Let's wait for the others. Okay, I have two answers already. Team C, careful with your units, ano? Oh, well, actually, hindi mo linagay kasi yung units eh. Okay, so yeah, the correct answer is, so ang nakakuha was si Albert at saka si Team C, ano? Your ID is going to be 2.25 MA, and then your output is going to be 7.5 volts. Okay, so just very quickly for the benefit of the others that didn't get it, no? So again, no, at Vin equal to 6, okay, ID, okay, so first we assume, remember, we assume first that saturation, okay, so ID is equal to 1/2 K VGS minus VTH squared. So this is 1/2 times 0.5 M. Okay, VGS is 6 minus 3 squared. Okay, and this will come out to be 2.25 MA. Okay, so I now compute for V out, which is equal to VDS. This is VDD minus ID RD. So that's 12 minus 2.25 multiplied by 2, okay, or 12 minus 4.5, which is equal to 7.5 volts. Now you have to check, again, no, check. Is VDS greater than or equal to VGS minus VTH? Itong VDS natin is 7.5. Our VGS is 6, VTH is 3, so the answer is yes. And therefore, tama itong mga values na to, no? Therefore, this is correct and this is correct. Are there any questions? Any questions? Okay, let's go to the next, ano? So at Vin equal to 8 volts. Again, no, let's assume saturation. So again, ID is equal to 1/2. Okay, diretso na natin, 0.5, 8 minus 3 squared. So what is this? This will give me 6.25 MA. And V out is equal to 12 minus 6.25 multiplied by 2. Magiging negative, no? Because 6.25 multiplied by 2 is 12.5. No? So this becomes minus 0.5 volts. Actually, dito pa lang, there's already a warning sign. Ano? Kasi paano magiging negative to? No? Your supply voltage is positive. Your input voltages are positive. Where will a negative voltage come from? So that's already a warning sign. No, but let's say let's say you don't have a good feel for these things yet, no, because getting a feel for things is something that comes with experience. Then you do your check. No, is VDS greater than or equal to VGS minus VTH? This is this is minus 0.5 volts. This is 8. This is 3. Obviously, no. No, it is not. No. Therefore, assumption is wrong. The assumption is wrong. The transistor is linear. So the mode is linear. So anong value ngayon ng I sub D? Ang kailangan natin gamitin equation ngayon is I sub D, okay, is equal to K VGS minus VTH minus VDS over 2 multiplied by VDS. Okay, so this is yeah. So this is 0.5. VGS minus VTH. VGS is 8. VTH is 3. 8 minus 3 is 5. 0.5 times 5 minus VDS over 2 multiplied by VDS. But how do I solve for ID when I don't know what VDS is? So, in effect, I cannot solve for ID unless I know what VDS is. Fortunately, we can form another equation. No? So this is one equation. That's equation 1. The other equation we form is using KVL dito sa drain to source path. No? So using KVL, okay. What is ID? ID is VDD minus VDS divided by R sub D. No? This current ID is VDD minus VDS divided by R sub D. So this is 12 minus VDS over 2. So this is my second equation. So I have to solve these two equations simultaneously. So let's do that. I'm going to get 12 minus VDS over 2, that's ID, is equal to 0.5 5 minus VDS over 2 times VDS. Notice that this is going to be a quadratic equation. What is that quadratic equation going to look like? I have it written down somewhere here. It's going to look like this, 0.25, yeah, 0.25 VDS squared minus 3 VDS plus 6 is equal to 0. Yung 6 galing dito, no? Yung 12 over 2, that is 6. Yung 0.25, that is 0.5 times 1/2, no? 0.5 times 1/2 is 0.25, then you have your VDS squared, no? And then this is 2.5 VDS plus 0.5 VDS is 3 VDS, and then lipat natin sa kabila, nagiging minus 3 VDS. So using your calculator, you can get the roots. No? You're going to come up with two solutions. You're going to come up with 9.46 volts and 2.53 volts. Now, only one of these is going to be valid. No? If I use this, no, here, the transistor will be in saturation. If I check this, here the transistor is in linear mode. No? So obviously, ito yung tama. Because we already said that the transistor is not in saturation. That's why we used That's why we ended up using the linear equation. So when I got my two solutions, ito, pwede kong i-eliminate. So this is wrong, and this is correct. So VDS is equal to 2.53 volts. No? Sorry. So this is going to be 2.53 volts. No? And you can compute for I sub D. I sub D is VDD minus VDS over RD. So that's 12 minus 2.53 all over 2. And I'm going to get, sorry. I'm just going to get 4.73 MA. 4.73 MA. Are there any questions? Any questions? So I'm pointing out the importance of checking. No? That's what I want to point out here. You have to check that your assumption is correct. No? So here we saw that the assumption is wrong. So we had to shift to linear mode. And when you shift to linear mode, you end up having to solve for two equations in two unknowns. And the solution ends up being quadratic. And because your solution is quadratic, you're going to come up with two roots. And then you have to check which one of these roots is valid. Which one of these roots is valid? Only one root will be valid. And yun yung tamang sagot. Now, I want to warn you about something. Many of you are fond of using the solve function of your calculator. I encountered that teaching in the past, that many students are fond of using the solve function of your calculator. In other words, itong equation na to, hindi nyo gagamitin yung polynomial function ng calculator nyo. Ang gagamitin na lang ninyo is your solve function. And there's no problem with that, except that you only end up with one root. No? Well, actually, you can experiment with different starters to end up with different types of roots. But usually, you only end up with one root. And a common mistake of the student is, basta't nakuha na niya yung root na yon, yun na yon, hindi na niya chine-check. No? That's why when you have a quadratic equation like this, instead of using the solve function of your calculator, use the polynomial function para makita nyo lahat ng roots so that you can eliminate the wrong root. No? Otherwise, it's going to be hit or miss dun sa solve function. You understand what I'm trying to say? Naintindihan nyo? Okay, I'm going to stop here first. No, what I want you to do is I want you to try filling in these last two. No, I'll post the slides. Ipopost ko sa Uvle, no. And then try filling in these last two. Okay, and then checking it against this, checking it against this, no. And then I'm going to forward to you all of the slides already so that you can also read up in advance. Now these are my slides. They are not the official slides of the course. The official slides of the course you can pick up in Uvle. So this is really just a supplementary lecture, no. Yung official yung nandun sa Uvle. Okay, so that's where I'm going to stop now. No, so there's a question. Yeah. So sorry, no. This should be K. You're right, no. This should be K. Thank you for catching that. No? Let me correct that now. Any other question? Actually, kaya nagkakaroon ng confusion kasi some books, yeah, I might as well mention that now, no? Yung ibang libro, okay? Yung ibang libro ganito, no? ID is equal to 2K VGS minus VTH minus VDS over 2 VDS. And then this is for linear. Saturation, you have ID is equal to K times VGS minus VTH squared, no? And then some books have it this way, no? ID is equal to K VGS minus VTH minus VDS over 2 VDS 1/2 K VGS minus VTH squared, no? So it really depends on how K is defined, no? It really depends on how K is defined, no? So in some books, they will define K such that ito yung mga constants. In other books, they will define K such that ito yung mga constants. I think, no, personally, I think that it is better to use this, no? Because then your value of K, which is called the process transconductance, becomes directly proportional to the dimensions of the transistor, no? Anyway, it's something that you're going to learn in your future courses, but sometimes there's some confusion there, no? So in my slides, this is what I use. In the text that we use for EEE 131, this is also what is used, no? But in some of the previous lectures of 1, 2, 3, ito yung ginagamit na equations. So just make sure that you know how K is defined. Anyway, thank you for bringing that up. Any other questions? Okay, so that's all for today. We'll continue on Tuesday. So I will sign off as soon as the last person leaves the room. Okay, thank you.
Thank you po, sir.
You're welcome.
Thank you po.